I'm going to go through A-level chemistry paper. This is the Edexcel paper, paper 1 from June 2018. Okay, I've done the first half of this paper already in another video. So questions 1 to 7. So starting off here with question 8. Okay, this question is about ions and ionic compounds. The first three ionization energies of calcium are shown below. Complete the table by identifying the specific orbital. Right, so calcium, if you look in the periodic table, calcium is in period 4 and it's in group 2, so it has got it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the first ionization energy, the electron is coming from the 4s orbital. The second is also coming from the 4s, and then we get a big jump there. I'm just going to ask about that in a minute, because we're not going from the 4th quantum shell, but the 3rd quantum shell from the 3p shell. An equation for the third ionization of calcium. So it's going to be Ca2+. And don't forget, you need to have the gas symbol in there, gaseous sign. So already lost 2 electrons, removing the 3rd electron, Ca3+ gas, and an electron. Okay, so why the difference between the 2nd and 3rd ionization energies of calcium is much larger than the 1st and the 2nd? Okay, so when you take the 2nd, the 1st and the 2nd are both from 4s. So they're both about the same distance from the nucleus, and they've got the same amount of shielding. But the 3rd one comes from 3p. It's a new quantum shell. I'd probably use that term. Different quantum shell, which is closer to the nucleus. So the attraction for the nucleus is a lot stronger. So you get a big increase. It's like 4 times higher than the 2nd. So important to name the orbitals which those electrons are coming from. Right, we've got a Born-Haber cycle here. The energy changes are given in kilojoules per mole. What is the value for Y? So we want to find out this, and this one here is Y. And of course, that is the first electron affinity. You're sticking an electron onto a fluorine atom. Now, the whole point of drawing a Born-Haber cycle is in a diagram, rather than just drawing, like a normal Hess's law. The point of doing it is in energy here, so that you don't have to worry too much about the signs. You can visually see what's going on. So without worrying about the signs, if we just add up that 79 for that, and that, you will get 1374. So that all of that there is 1374 kilojoules. And this bit here, they tell us, is 1031. Don't worry about the sign. So that means we know that this bit here has got to be 1374 minus that, which is equal to 343. Now we have to think about the sign. Is it plus or minus? Well, the arrow's going down, so that's exothermic. So we say the sign is negative. That's the way I would do it. Don't worry about the pluses and minuses until right to the very end of the calculation. Okay. Right. Now we're talking about the difference between theoretical and experimental lattice energies. Comment on the theoretical and experimental differences between them, giving reasons for any similarities. Well, the experimental is obviously the true value. The theoretical, it's important to state, is calculated on the assumption that the ions are all spherical. Okay, so they're not distorted in any way. And so, i.e., the compound doesn't show no covalent character. Get all those terms down just to be on the safe side. Now, if we look at lithium chloride, there's a good agreement there. They're very close. So we can assume there that we can say that the assumptions are correct. There is no covalent character. There's no distortion of the ions. We look at magnesium iodide, there's a big difference, okay? And that means there is some distortion going on there. There's some covalent character. Now, why should that happen in magnesium iodide rather than lithium iodide? Well, small, highly charged ions, highly charged positive ions cause distortion. If we look at magnesium, magnesium is going to be 2+. Okay, yeah, it's bigger than lithium because it's about lithium's only 1+. So I think we've got to say that Mg2+ has got higher charge density. So it's better at causing distortion. And also we probably need to mention here, this is 6 marks, there's a lot of marks going for this, is why is the iodide easier to distort than the iodide ion is easier to distort than the chloride ion. Right, so iodide is a big ion, chloride is going to be a lot smaller. So it's easier for the positive ion to attract, we've got a positive ion now, just rub that out. Got an Mg2+ ion there. It's easier for that to distort the ion and pull it over because the nucleus of the iodine is a long way from the outer electrons. So large negative ions easier to distort, and iodide is larger than. Right, because the outer electrons further from the nucleus, the positive nucleus, and there is also more shielding, so the nucleus can't hold on to them as strongly. Okay, so quite a long answer to that question there. Right, I'm going to have to make some space there, get rid of that. Right, the next question then is about entropy, number 9, and free energy. Complete the table giving the sign of the entropy change of the system. Okay, the entropy. Right, so we can see with this one, we're going from a solid, highly ordered solid to a gas. So it's definitely going to be an increase in entropy, so it's going to be positive. Here we're going from a highly ordered ionic solid to the ions all floating around separately in water doing their own things, so that's much more disordered. That's going to be positive. The last one is a bit more difficult. They're all gases, but we've got 4 moles of gases on this side and only 2 moles of gas on that side, so there is slightly less disorder on the right hand side, so it's going to be negative. Okay, calculate the total entropy change for the thermal decomposition of calcium carbonate. Okay, the total entropy change. Okay, so what we need to do, well, they give us the delta S for the system, and they give us delta H. So total delta S total is equal to delta S of the system plus delta S of the surroundings. Right, so let's delta S of the surroundings. Is given by negative delta H of the reaction divided by the absolute temperature. Okay, so in this case, delta H is plus 178, so that's going to be minus 178 over the temperature, and the temperature is 298 Kelvin. Okay, so that is equal to, right, actually I need to be careful here because we need to convert this into, we should really convert delta H into kilojoules, into joules, so it's given, because delta S is here is in joules, so I'm going to convert that, so that's 178,000 joules, because of 178 kilojoules, and that is equal to, 597 joules per mole per Kelvin. So now we've got to put our numbers into this equation now. So delta S total is equal to the system 160 plus the surroundings, that is minus, so plus minus 597, that is equal to minus 437 joules per mole per Kelvin. Okay, moving on. Okay, so the reaction of sulfur dioxide with oxygen to form sulfur trioxide, they give us delta H and they give us molar entry values. We've got to calculate delta S for the system. So delta S for the system is equal to the sum of delta of S products minus sum of the S of the reactants. Okay, so let's see. On the product side, we have got 2 times the value for SO3, so 2 times 95.6 is 191.2 minus, now we've got to do 2 times the value for SO2, so that's 2 times 248.1. That's 496.2, and then for the oxygen is 205. So that's 191.2 minus 701, and that gives us a value of minus 136. Hang on a minute. So 191 minus 701.2, 510. Joules per mole per Kelvin. $510. Okay, that's right. So it's a negative value, 510 joules per mole per Kelvin. Sorry. Yeah. Now the next part of that question is working out a value of delta G. Calculate the free energy change at 298 and deduce whether the reaction is feasible. So delta G is equal to delta H minus T delta S of the system. Right, now we need to convert our delta G is usually measured in kilojoules per mole, delta H in kilojoules per mole. So we need to convert our delta S value from joules per mole into kilojoules per mole per Kelvin. So there's our delta S value. Convert it into kilojoules is 0.51 minus 0.51 kilojoules per mole per Kelvin. Put the numbers in. Delta G is equal to delta H is minus 288.4 minus where the temperature is 298 Kelvin. 298 multiplied by minus 0.51, that's minus 288.4 minus minus, that works out to be 100 minus 151.98. Of course, that's going to become a plus. So delta G is equal to minus 136.42 kilojoules per mole. Right, it is a negative value, so that means the reaction is feasible. Delta G has got to be negative for the reaction to be feasible, so it is feasible. All right. Right, let's get rid of clear a bit of space. Oops. In industry, the reaction is carried out at 700 K using a vanadium 5 oxide catalyst. Calculate the value of the equilibrium constant K at 700 Kelvin. Well, we need to know the formula there for delta G and K. So delta G is equal to minus RT ln K. Ln is the natural log of K. Right, so rearrange that. We get ln K is equal to minus delta G over RT. Put the numbers in. So we've got, now we have to be careful again because R is in joules per mole. That's 8.31 joules per mole per Kelvin. Whereas delta G this is in kilojoules, so we need to convert our delta G into joules. So that's going to be 60,000 joules per mole. Put the numbers in, minus 60,000 over 8.31, and the temperature 700. So work that out. We get ln K is equal to 10.31. Now we need to find out K. So if ln K, ln is log to the base E, so that means K is equal to E to the power of 10.31. So you want to use your shift ln, anti-log if you like, sometimes you can call it, shift ln button on your calculator. So shift ln 10.31, and that will give you an answer of 30,169. That's the answer. Okay, so if you don't do maths, then you just have to make sure you know how to work out your logs and do the reverse of finding a log to be okay with that question. Right, the equilibrium constant has a larger value at 298 than at 700. Explain. So you will get that means, so equilibrium constant is bigger value. That means you're going to get more products. So at equilibrium, which you want products. So why do you do it? Why don't you do it at at the temperature, at the lower temperature of 298? Well, this is a fairly standard question, isn't it? And it's because the rate of reaction would be too low. So you would get a good yield at equilibrium, but you'd have to wait a long time for it to reach equilibrium because the rate would be too slow. Okay, now the final question on this paper is a really quite a tricky, complicated titration sort of analysis using titration question. So we'll head towards the last bit here, where okay, and then we'll answer some of the intermediate questions on after that. So it says yellow gold is a mixture of copper, gold, and silver. Okay, and we want to find out the percentage of gold by mass in the sample. That's the aim of, that's what we're doing here in this question. Okay, so the first thing they do is they dissolve the metal in conch nitric. Only the copper and the silver dissolve, and the gold is left behind. Okay, and that gives you the equations there. So the copper is oxidized to copper 2+, the silver is oxidized to Ag plus Binitric acid is a pretty strong oxidizing agent, right? So dilute it with distilled water and filter the gold off. Get rid of the gold. Okay, then what they do is they add HCl to the filtrate. Now HCl will precipitate out all the silver ions. So, and they give us the mass of silver ions there. So the mass of silver chloride. So let's work out how many moles of silver we've got there. So that would be the first thing to do. So we're going to get moles. We work out the moles of silver chloride. We can work out the moles of silver, and then we can work out the mass of silver in the sample. So the moles of silver chloride is equal to mass over mR. We got 0.706 grams of that. The mR of silver chloride is 107.9 for silver plus 35.5. That gives us 143.4. Right, so work that out, and that gives us a value of 4.923 times 10 to the minus 3 moles of silver chloride. So therefore we can say, therefore, the moles of silver in the sample is the same as that. So we can work out the mass of silver in the sample, because mass is equal to moles times mR. Let's do that. So mass of silver, moles times mR, AR I should say, atomic mass of silver. So that's 4.923 times 10 to the minus 3 multiplied by 107.9. That is equal to 0.531 grams of silver. So I'm going to write that up there so you can find that. So Ag mass is 0.531 grams. Okay. Now the next step is to find out how much copper we have got in the sample. Okay, that's a bit more complicated than that one. Okay, so how do we find out the mass of copper? Right, so you've got copper 2+ ions in it, okay, and you're going to react them with an excess of iodide ions, and this makes iodine. And then we can find out the number of moles of iodine we've got by titrating the iodine with thiosulfate. So what you would do there is, you've got your, I draw a little picture so you visualize it. You've got your conical flask, and this has got iodine in it. And here we're going to put thiosulfate in there, S2O32 minus. The concentration of the thio is 0.1 mole per decimeter cubed, and we needed, it says, 39.4 centimeters cubed of copper sulfate, of thiosulfate, sorry, for the titration. Okay, just to remind you how this works, this titration. So iodine is kind of a dark brown color. As you run in the thiosulfate, that's going to go paler and paler as you use up the iodine. The iodine's turned into iodide, sorry. And just when it gets very pale, then you add a little bit of starch, and it tells you it adds starch. That's the indicator. And that makes a very dark blue color, really strong dark blue color when you put that in. Very intense, even at very low concentrations. And so you just at the end, you put that in, and then the end point you want is when that blue-black color disappears. When it goes blue-black, disappears. And that's a question later on. Ask you what the indication of blue-black color disappears is the end point. You can do it without an indicator. Just look for when the brown color disappears, but it makes it much easier to spot by intensifying the color by adding the starch. Okay, so let's do the calculation there. How many moles of thiosulfate have we used up then? So we do that concentration times by the volume, 0.1 times 39.4 over 1,000. That gives us 3.94 times 10 to the minus 3. Right, let's look at this. The ratio here is 2 moles of thio react with 1 mole of iodine. So mole of iodine then is going to be half that. So the moles of iodine we had, 3.94 times 10 to the minus 3 over 2, which is equal to 1.97 times 10 to the minus 3. I'm just going to rub this out here now. Okay, right. Now we need to go to this equation now. This gets complicated. Look, every mole of iodine you get comes from 2 moles of copper 2 plus ions. So the moles of copper 2 plus ions that came from, we've got to double that, 1.97 times 10 to the minus 3 times 2. That takes us back to 3.94 times 10 to the minus 3 moles of copper. Okay, so we can now work out the mass of copper there. So one mole of copper metal gave us 1 mole of copper ions. So the mass of copper metal in the original sample then is going to be moles times by the AR of copper. So that's 3.94 times 10 to the minus 3 multiplied by the AR of copper is 63.5. That gives us a mass of 0.25. I'll just work that out. Okay, 3.94 0.250. Okay, 0.250 grams of copper. Right, now we know the moles of mass of silver, so that's the mass of copper. The mass of silver from earlier on, and the total mass I'll write down here as well. So the mass of silver we worked out, if I just scroll up a bit here, well, it was 0.531 grams. We worked it out. Okay, 0.531 grams. The total mass was 0.706. So let's work out the mass of gold. All we've got to do is we've got the copper mass here, we've got the silver mass, and we've got the total mass. So mass of gold total mass, which was 0.706, minus the mass of silver, 0.531, minus the mass of copper, 0.25. That is equal to 0.468. Okay, now we have to work out what percentage of that, no, that's not right, sorry, it's not right, is it? 1.25, sorry. I've got the total mass wrong, haven't I? That was the total mass was 1.1.25, 1.250, not what I said it was down here. Sorry about that. 1.250. So that is going to be 1.250 minus those is 0.468. So now we need to work out what is the percentage of gold in that. So the percentage gold is equal to the mass of gold, 0.4688, over the total mass of the metal, 1.250, multiplied by 100 is equal to 37.5%, which fortunately is one of the alternatives that they give us here. Well, and so you'd say, determine using experimental data the carat of the sample of gold. Well, it's 37.5, so it's 9 carat gold in that case. The other questions they asked there, I've answered them already. Oh, we'll set to one of them I haven't. Let's just have a look here. Right, I haven't answered that question. Write the equations for the reaction of copper with nitric acid using the half equations given in step 1. Okay, now let's go to step. So here's our half equations. I'll just cut and paste those. Right, put them in there. Right, which ones do we need? The reaction of nitric acid with copper. So here is the copper, 1, 2 electron process, and the nitric acid, this one here is a 1 electron process. So we have to multiply this one by 2 before we add them. So we add them together, we're going to get 2 copper plus 4 nitric acid goes to copper 2 plus 2 nitrate ions, 2 NO2 gas, and 2 waters. And that's the end of that paper.